of you. So I'm going to talk about work that we've been doing in Zurich, Joanne Liu and Philippe Marty on early Earth dynamos, and it will rapidly become apparent what I mean by an early Earth dynamo. It is geometrically different from what I would call the mainstream, which is the present the geometry of the Earth. It's got a different geometry, a different mode of heating. Is 100% clear on this. It probably represents something like 80% of Earth history, and that is the period of Earth history when there was no inner core present. But we can discuss whether that number is correct or not. So there is essentially two parts to my talk. Part one is about viscous dynamos, and part two is about unconventional dynamos, or if you wish, part one is about unconventional dynamos and part two is about unconventional dynamos. So the present day geometry of the Earth is that, and that is where most of our numerical efforts go. But I'm going to do the following. I'm going to get that inner core out of there, and I'm going to be working on the blue blob, which you could call the canonical geometry, because there's no radius ratio to worry about. It is just the ball, or the full sphere. And I'm actually often asked by people in geosciences outside our subject, and I think it's a very reasonable question. They've asked me, is there a problem? Is it possible to generate the magnetic field in the period prior to the formation of the inner core? And I reassure them and say, no problem. You can, I mean, mechanistically, you think there's no problem, and theoretically, you believe there's no problem. But actually, when you come down to it, the evidence is rather scant, and I'll show you the actual evidence. So the difference in this in what I'll show you is that the heating mode is one of internal heating, which is the same as if you have secular cooling of the entire Earth. So what we have is the equivalent of an entirely uniform heat source throughout the ball. Right, so just a bit of geophysics, and we can debate these numbers, but as this is my understanding of where we are, there was a radical rewrite of the position on Earth parameters about 10, 12 years ago. So the latest ab initio calculations put the thermal conductivity at something like 120 watts per meter per Kelvin. It's about 3 times higher than we always thought. The original number being due to Stacy and due to a lot of analogies with general Earth material, general metals. So roughly, if the whole Earth is convecting and the heat flow down the adiabat is about 15 terawatts, then the time to grow the inner core to the present size is something like 600 million years. And I don't want to personally stand by these numbers. These are what you will find in the literature. I believe they might be quite imprecise, but the point is that these numbers tend to make the inner core rather young. That is why I say to you that what I want to present is probably representative of the other 80% of Earth history. Right, now, so we're on to part one then, which is the I'm going to talk about viscous dynamos. And I alluded to the fact that the evidence behind my assertion that there's no problem in generating a magnetic field is the evidence is scant. So it is a strangely unexplored problem. So Sakuraba and Kono in 1999 were the first to consider dynamo-generated fields in the sphere, or the ball, and they concluded that results were similar to the shell, but we'll return to that point because it doesn't really agree with what we found. And then really the next exploration was by Philippe Marty, who provided the benchmark dynamo in the ball. So that's a useful benchmark. Anyone who wants to do these calculations can check their code against that benchmark. It's a perfectly periodic solution. And then most recently, Melis Landau and collaborators computed in 2017.
Dames en heren, over enkele ogenblikken bereiken wij Aken. Uit zeer geneigd danken u alvast dat u de internationaal heeft gegaan. Tot ziens. Ladies and gentlemen, next stop in a few minutes, Aachen Central Station. If you leave us here in Aachen, thank you for choosing Deutsche Bahn. Take care. Goodbye.
Tau eta as the time scale. I'll use the essentially Alsatian units for the magnetic field. There's a special unit for the temperature field, given that the solution is internally heated. And so I hope you'll all agree that these are the governing solutions, the way I've done it. So what we have here is the E eta, which is the magnetic Ekman number or the magnetic Rossby number, whichever you like. It stands out here at the front. The Coriolis force is order 1. Here's the thermal driving. Here's the Lorentz force, and so on and so forth. We've got the induction equation, and we've got the temperature equation, and we've got boundary conditions. I'm going to have uniform temperature boundary conditions, electrically insulating conditions on the magnetic field. And then I'm going to have either no slip or stress-free conditions, and I will try to flag those up so that you're all aware what I'm doing. I'll try to flag those up. So here are the 4 non-dimensional parameters, the modified Rayleigh number, and then the 3 small parameters, some of them smaller than others. So the Ekman number, which is tiny, measuring viscous force, is the magnetic Ekman number, or if you wish, the magnetic Rossby number, E eta. This is a crucial parameter, something like 10 to the minus 9 in the Earth, and the Roberts number, the ratio of the diffusivities. And I'll sometimes use these other quantities, which perhaps people prefer. PM is the ratio of the 2 Ekman numbers, and PR is related to PM through Q. Right, so the benchmark solution. So this is essentially a very useful and very exact solution to these equations in the full sphere, published by 2014. You can use it to check your own results. This is then the radial field on the core mantle boundary from this benchmark solution, and it's a repeating solution. It's an exact repeating solution, so you can derive some frequencies from it, and well, I think the benchmark paper was a very useful thing for everybody to try to check their codes with. So that is a pretty decent full sphere internally heated dynamo. And if I go back to my slides, you'll notice that up here I put SF, which is to remind me to tell you that solution is given, and it has stress-free boundary conditions. And some people hate us for that, but anyway, it's a bit awkward, but that's a solution with stress-free boundary conditions. It's actually the only stress-free solution I'm going to show you, because the rest of what I'm going to talk about is for non-slip boundary conditions. Now, Melis Landau was only 5 years ago published her work. You see NS at the top right says that this is non-slip. This is a non-slip solution, and they found a weak strong field transition, and that in their models occurred between 1 and 2 diffusion times. And this is actually a rather awkward element to this problem, because they saw that, and indeed we have seen the same. So this is our own computations, again, no slip. We're at a fairly modest Ekman number, 10 to the minus 4.5 there. You can see the rest of the parameters. And what do we have on these plots? The top plot shows you in blue, the magnetic total energy, in orange, the kinetic total energy. Time is on the bottom. This is now 4 magnetic diffusion times. It's quite a long time. You'll see that, in fact, the solution climbs and saturates, and it stays in this very weak field solution space here for a long, long time. And then finally, it decides it will move up to the strong field solution, in which the magnetic energy is exceeding the kinetic energy. That's after almost 3 magnetic diffusion times, which is really quite irritating. But it backs up the Landau discovery, really, that there are these weak and strong field states. On the second plot here, we have the fraction of the field in a dipolar state, this so-called F-dip, and you'll see that in the weak field state, it is fluctuating and also quite low in terms of the dipole component. Then the strong field state is much more dipolar. And here is the axial dipole component G10. And you'll see that here over time, you actually have a reversal that takes place. In fact, then you get back to a time when there are many, many reversals before G10 becomes a strong component of the dipolar solution. So that is a little bit of a tricky aspect to this problem, because you probably have to compute for quite a long time to say whether things are really in a strong or weak field state. Anyway, here is an example of the strong field state. This is the radial field on the core mantle boundary. So red tells you the field lines which are entering the core, and blue tells you the radial field lines which are exiting the core, and it's a pretty decent dipolar dynamo. You might say it doesn't look anything like the present field, but of course it doesn't have to. It's not in a domain that is relevant to the present field. Now, we've tried to make a start on putting together a regime diagram for this problem, and it's quite heavy going. So what we have here is, I'm doing this now in terms of the magnetic Prandtl number and the Rayleigh number. The number of times the Rayleigh number is supercritical over its critical value, RAC, and all the crosses are failed dynamos. Therefore, this solid line demarks the boundary between the self-sustaining dynamos and those which are not self-sustaining. The diamonds are unfortunately multipolar dynamos, and but it remains to be seen that if you were to compute them for longer, who knows, maybe they would actually become strong field dynamos. The dotted green line is the green line that I'll show you on the next slide. So this is Ekman 10 to the -4. The next slide is for a slightly lower Ekman number. The dotted green line is the minimum magnetic Prandtl number for dynamo action in the shell as determined by Uli Christensen and Julian Aubert. PM min is 450 e to the 0.35. So you can see that dynamo action is harder in the full sphere than it is in the shell. And the two big circles are the strong field states. So the size of the symbol is to tell you how strong the field is. And you can see that you've got these two strong dipolar states. There's a bunch of multipolar weak field states. I think this behavior of the ability to have two states is a problem. So I guess we need to then compute these for even longer to discover whether they could become strong field states or not. Okay. So that's about everything I want to say about viscous early Earth dynamos. It is indeed possible to generate a magnetic field for the other 80% of the Earth history that you need to do it for. So let's talk in part 2 now about the unconventional dynamos. And this is work that has grown out of a long collaboration that involved Quan Lee and Phil Livermore in the past. And then we've worked some more in the PhD thesis of Joanne. And it is further simplifications to the problem. So I'm going to simplify this problem even further. I'm going to now make a reduced model in which I filter out inertial waves. This is going to be an inviscid model where I remove viscosity, and I call it the Taylor-Brzezinski system, which you will see. You see why in a moment. So it really builds on the work of Brian Taylor and then Stanislav Brzezinski, who passed away last year. We keep pure alpha waves in the system, which are the torsional oscillations. The filtering operations that we make means that the system still retains the MC branch of the waves and I hope I can give you cause for optimism in the preliminary results that I show you. So let's just try to, I mean, this will be familiar to many people in the audience, but let's just try to tell you what I'm trying to achieve here. So you have the joy of consuming my hand-drawn diagram. It's a sort of picture of how I see things operating in the course. So you have we're thinking here about very long time scales. We're thinking about the diffusion time scale and the ability to have dynamos survive for all of Earth history. So I see it that there's a very slow manifold that is generated by the convection of the Earth and the large scale flows, and probably also including the MC waves in there. And then on top of that slow manifold is some wiggles associated with torsional oscillations. And now if we were to look inside one of those boxes, blow it up in time and see what else is there, you would see the inertial waves wiggling along. And if you were to take another box and blow that up, you would ultimately see the acoustic waves. Right? Now, we're all happy about the fact that we're going to filter out acoustic waves because we're not interested in them. We don't think they play a role. We're also going to filter out the inertial waves. And the only thing that I'm trying to grab onto is this sort of slow manifold on which the torsional oscillations sit. And my reason for doing that is to make, well, I think it's realistic. The torsional waves, as we know for the Earth, start out life maybe at around 6 years from the discovery by Rayleigh, and then of course their periods become longer and longer. So this is just a recap of the governing equations, but what am I going to do to the governing equations? Okay, I'm going to get rid of the inertial term here on the left. I'm also going to get rid of the viscous term on the right, based on the smallness of the magnetic Ekman number and the Ekman number. And of course, I'm going to end up with the system slightly modified from what Taylor wrote down, but it's essentially Taylor's system, I suppose, with Brzezinski's modifications. So we decompose the flow U into the ageostrophic component and then a zonal axisymmetric geostrophic flow invariant on cylinders in the phi direction. And we've lost all the acceleration terms here on the left. So we've turned this Navier-Stokes equation from a prognostic to a diagnostic equation. The flows are driven by the buoyancy and the Lorentz force. But what I've retained is the accelerations that can occur in the geostrophic component due to the geostrophic part of the Lorentz force. So we can excite the torsional oscillations that way. Of course, there are no fully geostrophic inertial modes. So this separation is entirely consistent. And many of the experts in the room will know the reason that I've done that, because that means I do not have to satisfy Taylor's constraint. I just let the Lorentz forces do whatever they want with the geostrophic component, excite torsional waves, and Bob's your uncle. So boundary conditions, right now, we're going to have a non-penetration boundary condition on the flow, and I'll signal that occasionally with an NP to remind you, and everything else is the same. So another remark is that when you work out the energy equations for this system, you can see here that all of the energy, the only way that energy changes in this system is through the changes in the magnetic energy and in the geostrophic component. There is no energy that's changing associated with the ageostrophic flow, which is a strange thing, but the ageostrophic flow is merely a slave of the magnetic field and the buoyancy. But nevertheless, I'll sometimes show you in diagrams this fictitious quantity, which is a measure of the energy in the ageostrophic flow, even though it's just a slave of B and theta. Okay, a couple of words on the computational scheme. So everything is computed here fully spectrally, and spherical harmonics in theta phi, and then we use the polynomials invented by Chris Jones, who's around it, and worked on by Steve Walland in his thesis. There's some special things we do to create sparse equations. Coriolis and mass matrices are sparse but large. There's a separate solve for each M, each azimuthal component in the Navier-Stokes equation. Just a few technical details, but these are very preliminary results. So it's probably well known to many of you that it's tricky to get onto the stable branch, because these are not solutions that can spontaneously grow in the absence of viscosity. So you have to actually start at a finite amplitude magnetic field, which we've successfully done. So here is an example of magnetic energy at the top. I call this the proxy for the kinetic energy. I'm showing you the quantity that I said I would define, even though there is no kinetic energy in this system. And this can be a topic for discussion. Perhaps someone will give me their insight into how that all works, but that's the truth of the matter. And then there's a sort of measure of thermal energy. So this thing has saturated nicely for more than a magnetic diffusion time. It's computed at a relatively low truncation level, and just remember NP top right means only boundary conditions we've got on the velocity field are non-penetration. There's nothing else. There's no viscosity in this system. So what about if I do the same at higher resolution? So I've done the same thing at 2 higher resolutions. So I think we've gone from 40 to L equals 40 to 60 to 80 up here. You'll see these are done at different truncations. I don't believe that we're fully converged yet, but you can see that it doesn't make much difference ultimately to the saturation level. What truncation level you work at. And you see here are the rapidly fluctuating on this scale, this proxy for the kinetic energy. Okay, so what kind of field do we develop? So that is a very highly dipolar magnetic field that is developed by this system. So the control parameters for this are, of course, Ekman number is 0, magnetic Ekman number is 10⁻⁶, Roberts is 1, Rayleigh number 2,500. This is only very slightly above what you would call criticality. Of course, you don't know what criticality is until you start reducing the Rayleigh number, and then you'll get to a value where the whole thing dies out. And the whole thing dies out a little bit, let's say just slightly below 2000. So this is only slightly sort of supercritical, if you wish. And it's got all the kinds of structures that you expect, really. So you can see, obviously, the strong columnarity here. This is the phi component of the velocity field. This is the field strength in the interior. And this thing contains torsional oscillations. So if you were to look at the geostrophic component, this is a time distance plot. So just to let you know what's going on here, this is S is the cylindrical radius. We're starting at S is 0.75. We're looking at the way that these geostrophic motions propagate in time. So they're propagating here through they're propagating in time through S towards S is 1, which is the boundary. And then the bottom half, I've actually flipped the scale so that, in fact, S now reduces from the boundary back into the interior. So you can see something like this big stripe here. It heads off to the boundary, and then you see it going the other way with a 180-degree phase change. So these things bounce right off the boundary. Perhaps unsurprisingly, there's only magnetic diffusion in this problem. There's no viscous diffusion. And another little thing of interest is you might wonder, well, how much of the energy is in the ageostrophic component and in the geostrophic component? So we've got this quantity R, measuring that. And in this table are the values of R for my 3 different resolutions. And you can see that R is it changes, of course, but it's reasonably stable around about 7 or 8. However, you can see that the ageostrophic energy is larger than the geostrophic energy. And the only reason for showing you that is that in the computations that we carried out, and as well were carried out earlier by Wu and Roberts in 2018, in 2 dimensions. So in 2-dimensional mean field dynamos, Taylor state dynamos, this was when we actually imposed Taylor's condition exactly. So there are no rapid oscillations of the geostrophic component, but the geostrophic component, of course, exists. In that case, it exists in order to make sure that Taylor's constraint is exactly satisfied. I wanted to just point out it's the opposite in those 2D mean field dynamos. There, the geostrophic energy dominates the ageostrophic. So things are quite different, and possibly they're a bit misleading, these 2D dynamos. Now, okay, top right, SF. What am I doing now? Let's take exactly the same parameters that I've just used for the inviscid dynamo, and let's reintroduce, let's now make it a conventional dynamo. Let's reintroduce viscosity. So we actually reintroduce both viscosity, we introduce the inertial terms. So these are the same values of the control parameters, and but I have to now have a stress-free condition. And I I introduced a stress-free condition. I think, well, stress-free condition is probably the closest I might get to my inviscid dynamo with only a non-penetration condition. So let's just now compute that dynamo for those parameters. And this is the thing that you get for this dynamo. And it's rather surprising. So let's just concentrate on diagram B here, which shows you the strength of the magnetic field. And this is not a dipolar dynamo. This is a hemispheric dynamo for those same control parameters. So the same control parameters that generated a pretty strongly dipolar field in the inviscid case generate this kind of behavior, a hemispheric dynamo in the viscous case. Which is what I've just said. Right, so those are preliminary results I thought I would share with you. Right now, I can't do the diagnostic solve at a higher resolution. I've shown you that actually things are not changing terribly already in the resolutions that I'm computing, but this diagnostic solve is well, something that we can fix, but at the moment the solve is difficult because of the distribution of everything onto multiple processes. So I think that's pretty much it. We know the Earth successfully generated its field over billions of years, during which it was in a full sphere geometry. The secularly cooled dynamos operate as dipole-dominated fields in the inviscid case. You've seen that in the viscous case, it's a bit more of a crapshoot, actually, and it's a little bit more tricky because you've got these weak and strong field states that take ages to decide what they want to be. And many of the dynamos in the viscous case are multipolar. And then the last thing I've just shown you is that this inviscid limit stabilizes dipolar fields when the viscous case does not. In other words, Ekman number 10⁻⁵ happens to be, for these internally heated dynamos, vastly different to the inviscid case E = 0. Thank you.
Thank you very much. Most impressive. Questions? Yes, Kathy.
Let's look at it again just for old time's sake. It's a funny one because, in fact, things do head sort of drift east, but then you'll find that they start off, they emerge again further west and then drift east. So it's a kind of constantly repeating conveyor belt. But you're absolutely right, Kathy. But I don't say that there's anything particularly special about this dynamo. We looked for a long time simply to find, we hoped we could find a nice sort of stable dynamo like Ully did for the shell case. We didn't find that. We found this one which is just constantly repeating. So at least it has measurable parameters. But I wouldn't say that that there's anything special about this. You'll have noticed that many of these dynamos, sorry, yeah, it's a oscillatory. I mean, it's not a purely traveling wave. You can see that it actually has more than one frequency in it. Actually, it's a complicated object. We haven't found anything tremendously simple in it. One of the things that you will have noticed, Kathy, that seems to be true of many of these dynamos is that much of the flux is located at higher latitudes. It's pretty much over the what we would call a tangent cylinder, where in fact present day we don't have so much flux. You don't have one, but it's where it's trying to create its own tangent cylinder. Yeah, it's a lot higher than it would be in the spherical shell case, which is probably to be expected.
So you did the unconventional conventional case, and you did the unconventional case. But did you do the conventional unconventional case and look at how torsional waves interact with, say, a tangent cylinder in the spherical shell?
Oh my gosh! Do you want to decode that? Are you wanting me to do the inviscid shell case?
Yeah. With the is that really hard to do?
Well, okay, I haven't done it, Steve.
Okay. Get on to
Really,
it.
really challenging.
Did you get a sense?
Dynamo in a blob.
Okay. Did you get a sense that without the inner core, it was harder to get an antisymmetric distribution of helicity? And is that lying behind the fact that it's more difficult to get a dipolar field, or did you not check that?
So I think it's too early for me to even answer that. I don't know. I haven't looked.
David?
So in your system where you throw away inertia and you throw away viscosity, but you don't have to apply Taylor's constraint, was that to make your life easy? Or if you could apply Taylor's constraint, would the average field still look like what you're getting? I mean, are these torsional oscillations crucial to the enterprise, or that Taylor's constraint is very hard to apply?
I mean, it does make life easier, but I actually think it still probably adds more realism. I think I used to be a devotee, but I probably think that actually having Taylor's condition equals 0 at all times is probably wishful thinking. I mean, I think this is probably more realistic. So, and it certainly makes life a lot easier. I think your question was, what's the difference? I cannot tell you whether or not imposing Taylor's condition will lead to the same solutions. In the 2D work we did with Cranley, in fact, so we did both in that case. And I mean, it is actually a little bit of a pain in the neck imposing Taylor's condition, but actually the results were largely unchanged. Actually, of course, in one you had the torsional oscillations, but they're very similar regardless. I think you asked me, I don't think the torsional oscillations play much of an inductive role. I don't think they're critical for the, yeah. Yeah. Yeah.
Having looked over all of these torsional oscillations, is the outcome the same?
I guess another way to phrase the same question would be, now that you have this Taylor-Braczynski solution, can you filter torsional oscillation out and look at the slow manifold that you were plotting in your cartoon?
Can you filter them out? In which way though?
As a post-treatment, now you've done the simulation, you've got 2 time scales in your problem. Can you extract the slow manifold from the simulation?
Well, the straddle manifold is I mean, it's there. Just
It's there plus torsional oscillation.
It's there
Can you
plus
filter
torsional
out the torsional oscillation and extract?
Yeah. The torsional oscillations are just UG. You just obviously just don't look at them, and then the rest is
No,
what
there's
you want.
there's a part of UG which is in the Taylor state. Can you filter out the
There's
oscillating
part of
UG?
UG that is.
The Taylor state. There's a geostrophic flow in the Taylor state. It determines the Taylor solution. Can you filter out the rapid oscillation in UG so as to get the slow manifold?
But there can be. I mean, there can be.
Okay. Seems to be something for the program.
Yeah, exactly. Yeah.
This is not a question, it's a comment about early Earth dynamos. The big problem is making sure that the core convex at all. And that's a highly non-trivial problem. The data show that the Earth had a magnetic field back 3.5 billion years, and there are people who claim evidence all the way through to zircons. That's controversial. But for most of the history, pre-inner core, we had a magnetic field. It was substantial. And so you need a dynamo, and getting the core to convect under those circumstances is non-trivial. Now, a central problem in geophysics is called the Urey number problem. The Urey number is the ratio of radiogenic heat production to heat outflow of the Earth. And there is no consensus about that number except that it's small, meaning that most of the heat that's coming out of the Earth right now is due to cooling. And that's cooling of the mantle, but in turn it cools the core. Those two are coupled. The mantle dictates the rate at which the core cools. It's difficult to have that progress all the way back through geologic time. And so we think that our scaling laws for mantle convection are in question. People like Shun Karanaga have worked on this. I'm not claiming we know the answer, but it could be related to the question of how plate tectonics works. But it is a serious issue. And it's interesting, I find it interesting at least, that when you look at the current Earth and think about how the current Earth works, as Andrew mentioned, we think it's inner core growth that's important, and a significant part of what's driving the dynamo is actually composition. That is the fact that the inner core and the outer core are of different composition. And compositional convection in planets is a very effective way of driving dynamos because planets are degenerate, meaning that you only need small density differences that come from composition to overwhelm the thermal differences that come from alpha delta T, where delta T is the amount of cooling and alpha is the coefficient of thermal expansion. So one of the issues is compositional convection. Last and not least, and you did mention this actually in connection with the choice of thermal conductivity, it's fascinating but true and troubling that if you look at the literature over the last decade or two, the thermal conductivity of the Earth's outer core has gone like that. Factor of 2. And a factor of 2 is what the game is. And it takes you all the way from cases where you don't have a problem to cases where you have a really serious problem. And people think they know the answer now, but I can tell you, measuring thermal conductivity of a liquid metal is exceedingly difficult, very, very difficult experiment, even at low pressure. And people have resorted a lot to the Wiedemann-Franz relationship, which connects the thermal conductivity to the electrical conductivity, but there's even some question about whether that applies to liquid metals. So this is a very interesting question. I'm sorry, it's a very long comment, but
No, thanks, Dave. Actually, I mean, I believe the data to be powerful. It says that we have had a dynamo in the early Earth. We'd better make sure we can explain it. The weaker data in this is the fact that the thermal conductivity comes from the ab initio calculations, 2 papers, both using the same code, VASP. It'd be great if this were actually done with something independent. VASP has got many approximations in it. So I don't know. Well, if the thermal conductivity is a problem, maybe it is not the correct answer. I don't know. You're looking skeptical there, Johannes. You're a devotee of.
I'm a devotee. No, well, I know, of course, that's a very interesting problem that Dave mentioned. But I mean, the tendency is that people believe the higher conductivity in the moment. There are independent ab initio calculations which point in the same direction. Maybe not all of them published, right? There are also experiments which show one or the other result. But as you mentioned, I mean, thermal conductivity is very difficult to measure, electrical as well, but not as difficult, I would say. So it's still, I would say, an open question, more or less. But I had a question to your talk. So these 2 states, the weak and strong state, you find a strong state is usually a sign that the magnetic field changes the flow and helps itself to create magnetic field, right?
Yeah.
And usually that happens easier if you increase PM. So I guess Emmanuel would agree. So my question is, if you have a larger PM and you just showed, close to onset, the PM values, if you choose a larger PM, if you still find the weak state or not?
Well,
Maybe you haven't tried.
But
So
I
maybe
mean,
you
I'm
should.
not in the business. I'm doing I was wanting to map out how the behavior works, but I mean, increasing PM, as we all know, is going in the wrong direction. Oh, well, we can, that's the topic for the, well, okay. Anyway, you can see that the strong field state, if you go to PM is 8, that's one of the examples of the strong field states. I mean, I'm not sure what you want. I think you said just make your life easier and increase PM. And
no. I mean, it's a double limit. You have two small parameters, E and E eta.
Yeah.
And it's the ratio of the two, as you've explained.
Yeah.
So you can have both tending to 0 with the ratio.
Yeah.
Maybe we've raised several points for the discussion that will happen tomorrow. So there were things on which there were clear disagreements. I can see a few hands, but I think we've had quite a few questions already. I propose that we continue discussion over lunch. So the lunch is taking place at Churchill College, which is right next to here. And if you look at your badge on the back, you have tickets. So the lunch is included. You can use ticket for the lunch. So we'll all go there, have lunch together, continue interesting discussions, and reconvene here at 1:45. Thank you very much. Thank you very much again.